Welcome to part 5. So far, we've analyzed rectangular tanks. Now let's ask a fundamental question in fluid dynamics. What happens if two tanks have the exact same initial water height and drain hole, but completely different geometric shapes? Tank A widens upward like a V shape, holding a large volume near the top. Tank B narrows upward like an inverted V, holding most of its volume near the bottom. Which tank will drain faster? First, let's look at the instant we open both drain holes at time 0. According to fluid mechanics, the pressure at the bottom depends exclusively on water depth h, not on the total volume or shape of the container. This classic principle is known as the hydrostatic paradox. Because both tanks start with identical initial water depths h, their bottom pressures are identical. By Torricelli's law, their initial exit velocities v and initial flow rates q are exactly equal. However, the moment drainage begins, their drainage behavior begins to diverge. The rate at which the water surface drops, dH over dt, is equal to the outlet flow rate divided by the tank's cross-sectional area at that specific height. Because cross-sectional area varies with depth, the water level in each tank drops at a completely different rate over time. Let's watch both tanks drain side by side. In tank B, the inverted V, the cross-sectional area at the top is very small, so its water level drops extremely rapidly at first in tank A. The top-heavy V, the huge surface area near the top causes its water level to barely drop initially. As time progresses, tank B's water head collapses faster, reducing its exit velocity earlier than tank A. Consequently, their drainage histories and emptying times are different. To summarize, first, shape does not affect initial bottom pressure or initial exit velocity. Both start identically. Second, shape does dictate stored volume and how driving pressure head evolves over time. And third, in a standard cylindrical tank, cross-sectional area remains constant, producing a steady relationship where the water level falls progressively more slowly as depth decreases. Shape doesn't alter the physics of pressure, but it governs the evolution of time. Now, here is the critical conclusion that many people miss. When you first watch both tanks drain, your eyes tell you that tank Y, the inverted V, is losing water faster. Its water level plummets rapidly because the narrow top offers very little cross-sectional area. The height h appears to collapse almost immediately. So your instinct says, tank Y must empty first, but that instinct is wrong. Here is the key physics. The exit velocity through the drain hole is governed by Torricelli's law. V equals the square root of 2 grams h. Velocity depends directly on the instantaneous water height h. In tank Y, yes, the height drops fast, but that rapid drop means the driving head h shrinks quickly, which means the exit velocity also decays rapidly. The tank is essentially starving itself of pressure head. In tank X, the wide top acts as a reservoir. The water level barely drops at first, so h stays large, and therefore the exit velocity stays high for a much longer duration. Think of it this way. At every single moment during the drain, tank X maintains a greater water height than tank Y. Greater height means greater velocity at every instant. Greater velocity means more volume leaves per second through the same drain hole. So even though tank Y's surface seems to race downward, the actual volumetric outflow from tank X is consistently larger throughout the entire process. Let us now watch the final phase of drainage. Tank Y's height has already collapsed. Its velocity is near zero, and it is barely trickling. Meanwhile, tank X still retains significant height, still has strong velocity, and is still pushing water out forcefully. Tank X crosses the finish line first. Tank X empties before tank Y. The V-shaped tank wins. Not because its level drops faster, but because its level stays higher, longer, sustaining a stronger and more consistent exit velocity. So here is the final takeaway. Do not confuse a fast drop in water level with fast emptying. The level can plummet, but if the velocity collapses along with it, the actual outflow slows to a crawl. What truly governs emptying time is the sustained exit velocity, and that velocity is proportional to the square root of the instantaneous height. A tank that preserves its height preserves its velocity, and therefore empties first. Tank X, the V shape, empties before tank Y, the inverted V. Height sustains velocity. Velocity wins the race.